Again, welcome. Today is Tuesday, April 27th. We still have another day in this month, and then we're going to be in basically toward the last stretch. So today's topic is on electrical current. And for that, you technically need a battery, okay? You need a bunch of other things also. You need I have in here resistors actually. These are color-coded resistors. I'm not familiar with them. And I was trying to build the circuit, but I couldn't find the battery holder so that I can connect the wire to the others. I have here a capacitor, which is part of the circuit also. And I have here a non-linear electrical device called a diode. So this is diode and transistors. They are part of the modern electronics, which is non-linear. And I have a bunch of other things in here. I was digging in there to see if I can build stuff out of them. I couldn't. And the biggest thing in here is, although I have wires, I don't have the battery holder for them. Anyway, how is everybody? How was the vacation and everything else? How was spring break? Everything was good? So we're ready to move?
It was nice not having to worry about lecture during the midterm week.
Okay. I'm not sure, honestly, if during the final, we're going to do the on-campus final for the other classes. If we do, then we're going to run into the same situation. If not, then we probably are going to continue the regular stuff with you guys. Anyway, but you were good. I mean, you were a little bit exempt from that thing in there. So let me share the screen. As mentioned, today's topic is on, let me move this a little bit closer in here so that they see. For some reason, a lot of people are not showing, and that's typical after spring break, but I was hoping that we have not that many low, basically, number. So again, we have, we're dealing with the electrical current because this stuff is coming in an exam down the road, so you guys need to be ready for it too, okay? So we have the flow of charges. That is basically what the current is. So if you have a charge sitting by itself, that doesn't do a current for you. As a matter of fact, even if a charge moving by itself is not a current. Just like as much as a car driving on the freeway by itself does not really make traffic. So in a sense, in here, current is similar to traffic. So you need a bunch of cars moving to really talk and say, you know what, I have traffic today. I have this in size of cars going. Same thing in here. You have charges in motion. That is what the current is. So when the power company delivers a plug for you and they tell you, okay, we're putting 110 volts or 120 volts on the wall, what they're saying is that they have a difference of potential ready to go, so to move charges, okay? So that is basically what this current is. Current is related to the voltage, and that's exactly what I was talking about in terms of 120 volts on the wall, or in the case of a regular battery, this is a D-cell battery, it's 1.5 volt, okay? So this is the voltage, this is what causes the current to flow in a conductor. Then we're gonna talk about the electrical resistance. Every material, regardless of how good of a conductor is, has a finite value of the resistance. These are typical resistors that I was trying to show earlier in the beginning in a circuit. I mean, this is a ready-to-go circuit if you look in the back. So the wires are connected to this junctions in here, and you can connect them in several configurations, okay? Then we're going to talk about Ohm's Law. Ohm's Law relates the current in a circuit to the voltage in the circuit, okay, with resistance. So that is basically what Ohm's Law is. We're going to talk about, there is a difference between this type of voltage, which is a direct current voltage. That means that there is a steady current going around from the positive to the negative. In reality, what's happening in here is that electrons are moving from the negative to the positive, but they are at steady flow, at constant rate, versus the AC current or the alternating current, the one that you get from your plug, and that one is actually going up and down. Sometimes when they tell you that we're delivering 120 volts to your household, what they're actually doing is they're putting at some point 170 volts up, and the polarity switches at some point to become 170 volt on the other end. So it's 174, 170 both ways, and it's fluctuating back and forth. On average, it actually acts like, not exactly, like 120 volts steady current or DC current. So this is basically the difference between the two. So one of them is time dependent, the AC current, and it's actually alternating in a fashion that looks like it's a wave or a cosine function, okay, periodic function going back and forth between the maximum and the minimum. And another one that is steady, DC current, direct current. So that's the difference between the two, okay? We're going to talk about the source of the current. Basically, that's the EMF, the electromotive force. And we're going to talk about the power, because at the end, when you go to the store and you tell them, you know what, I want a light bulb, the first question they ask you is what type of light bulb do you need? What kind of power do you need on the light bulb? Each light bulb has specific rating on its power. Basically, this is a light bulb in here. This is actually for demonstrations only, but different light bulbs have that too. If you look at any device, whether your monitor, whether your computer, whether you're a laptop, whether you're anything in there, in the back of it, usually near the power supply, there is a rating for how much power that device is going to consume, okay? And it's in watts. And it's critical, because the more that device is plugged into the wall, the more it's draining energy at that rate. So the rate at which power is consumed in a circuit is actually the power. But at the end of the day, the power company will only charge you for how much usage, the time that you use that power. So at the end, let's say, for example, you go and buy a 60-watt light bulb, and that will consume 60 joules in every second. So if you let it running for a minute, that's 60 times 60, that's 3,600 joules. So and so on and so forth. So the longer you're going to run it, it's going to consume that much energy. At the end of the day, the power company will tally that number and add it until you use this much energy. Therefore, we're going to bill you for this much. Okay. So versus if you go and buy, for example, a 100-watt light bulb, a 100-watt light bulb is going to consume 100 joules every second. So if you let it again running for 1 minute, that's 6,000 joules, okay? 60 times 100 is 6,000 joules versus 3,600 for the other one. So again, in this case, the power company will charge you for the actual usage, for how long have you been running that light bulb, or that computer, or that TV, or that refrigerator, or whichever equipment that is basically pulling the power from the power source, which is in this case the plug, okay? And we're going to talk about basically different kinds of lamps, LEDs, CFLs, and so on and so forth. And then we're going to talk about how is the wire connected in your household. There are two types of configurations possible. There is the there is a series, one after the other. I don't have, well, I did not bring any more wires. Here's another wire in here. I don't have another wire in here ready to go. I have a lot of them in the back. So if you take this one, for example, come on, connect it in here and connect to it another one in here. So now this side of this junction now is connected, as you can clearly see by this black wire. Now, if I take this side and connect it with this one, so the other sides are connected actually too. So what's going on in here? I have this resistor, so I don't have another wire to show that where this is coming from a power supply or something. But if this is coming from a power supply, the current will go through this one and then jumps here, goes to this one from here and comes to this one. So in this case, I could have it in a series, or I could have them actually in parallel, where I connect all of these wires to one side of a battery and all of these ones to the other side, and I will actually have them in parallel. In general, it's a combination of both. parallel series. We're going to see it schematically in here and how that works, okay? One of them, the series, will split the voltage between the different components and keep the current the same. And the parallel will split actually the current, but keep the voltage the same. That's the difference between the two. Okay. So again, this is a are you guys are looking at the slides I'm showing in here, aren't you? Flow of charge. Because it's very bad if I am talking about something and you guys are looking at something else. Yes.
The
Yeah, we can see
PowerPoint,
it.
yeah.
Okay, very good. Just to make sure, okay? Anyway, the point being in here is that this is basically, like, for example, there is a difference in pressure in here. If there is a difference in pressure, the fluid in here will move. Please don't push this mechanical system, the analogy with this mechanical system, into further more than that. Because there is a difference in pressure in here, there is a flow. Because there is a difference in potential also, so this is the gravitational potential energy actually of what's going on in here. The same thing for the other one. The other one is actually an electrical potential. So in order for me to maintain this flow, I really need a pump in here, okay? That is going to take the fluid from this point and move it. So it's needs to pump the fluid in here. And if I do that, then I will have a steady current. Because the water in here will fall on its own due to the difference in pressure, naturally. And that is the force of gravity that does that. Obviously, by these experiments in vacuum, not in vacuum, outside of the Earth, it's not going to work because there is no gravity to, so the fact that you have a difference in height doesn't mean anything when you don't have gravity. But with gravity, now there is this difference in height, therefore you have difference in pressure, therefore the flow will come in here. If you adjust the pump so that it accounts exactly for this difference in pressure, it's going to pump just the right amount. The minute the next basically drop of water comes in here, it takes it and pump it up. So in this case, we're going to maintain a steady current in here. So this is the analogy between a mechanical system using a pump and a battery. So the battery really is your pump in a circuit. So the battery acts just like the pump does in here, okay? Metals, in general, they have the ability to conduct electricity because they have electrons that are basically free to move. The matter is still neutral because I can take this copper wire, for example, and touch it. Let's not take that copper wire. This is metal. If I touch it, there is no current in it. There is no charges in it because it's neutral. But if I connect it to a power source, the charge in it starts to move. So any metal has that property. It has, because the electrons really do not belong to a specific atom, they belong to the community of the atoms. That's why they do that, okay? In fluids, actually, you have ions, like for example, in water and salt water or something like that, because you have Na by itself, which is a positive ion, and the chlorine by itself, which is a negative ion, and they can conduct electricity too. So that is two ways of conducting electricity, and it has to be with charged particles, whether through ionic conduction or through basically electrons inside the metal. Protons are too tied to, too bound to the metal, so that they can't do that. Okay. So the current is again the flow of charges. The unit for measuring the current is the ampere, and that's what you see actually also on the back of your device too. If you look at near the power supply, we have one in here that I can. What was that? The other one. No, this does not have any reading whatsoever. This is part of a circuit that I yanked out because actually the power supply is not even showing on it, okay? So the power supply was connected to maybe through, I don't even remember where I removed it from. The power supply actually is here, but it should be in the label somewhere in there, okay? Anyway, the point being in here is that if you look into any device that you have, your computer, for example, it should tell you in the back exactly what's the rating on that device, okay? In terms of how many amps and how much power also it takes. So it's measured in amps, and the amp is 1 coulomb per second. That is basically okay. So let's try to understand now what's going on inside the circuit, okay? So this is basically what you're going to have to basically summarize. What I'm talking about in the discussion below in this chapter, that's what you're going to summarize. So let me pick up a pen in here. So here is the situation. So if you take a metal in here, it's made up of fixed, basically, ions. I mean, they're agitated a little bit due to the thermal agitation, but you have charges that are typically electrons, and the electrons, due to the random motion, they are moving in every which way. So each electron could be moving one way or the other with different speeds. They don't even have the same speed. Some of them are moving too slow and others are moving too fast. And if you average this quantity, they have no velocity. So it's a random motion. So if you ask, why is it random? Why is it random? It's because of temperature, okay? Random motion averages to 0. Okay, this is before applying a difference in potential, before connecting it to a battery. Now, once you put a battery, let's say, for example, there is a 1.5 volt in here, battery. So charges now start to react to it. So it starts to move, actually, because of the electric field that is applied in there. So now a charge, like this charge in here, for example, starts to move until it hits an ion, until it hits, for example, if it's iron, until it hits the atom of the iron, okay? The nucleus of the iron, because the electron still belongs to it, but it's free to move, but it's still neutral. Since it has a less mass, it can move, but the atom itself, I mean, the nucleus itself is too heavy to move, so it's gonna stay in its place, okay? So in this case, this will move until it hits it. Once it hits it, that's it. It's going to forget everything it was doing before and come out in any direction that you are going you can imagine. So it's a random motion again. But then the minute it emerges after that collision, it's going to start to accelerate again. So let's say it's accelerating here, and then finds another ion, bumps into it, and so on and so forth. This acceleration between collisions, this is the drift velocity. And that is what causes current. Okay? The longer the time it takes for between collisions, the better the conductor. The shorter the time between collisions, the not so good conductor. As a matter of fact, it could be instantaneous. The minute it tries to accelerate, bumps to another one, bumps to another one, bumps to another one. So it's not going to go anywhere. Those are insulators, actually. They are not conductors. Like, for example, wood. So if you take a piece of wood and you apply potential across it, it should exhibit the same thing, because even in wood, there are electrons in there, although the electrons are anchored to their atoms, they really cannot move. When they try to move, then the atom will prevent them from doing so, okay? Anyway, so this is how conduction happens in materials. Because it keeps on bumping to all kinds of things, that is what actually the resistance is. So the resistance is how frequent each charge carrier, which is an electron for all practical purposes. The resistance is how often each charge carrier basically is slowed down by collisions with the ions, with the atoms, okay? Because atoms don't move. That's basically, in a nutshell, how electricity happens in the matter. Does this make sense, the picture?
Yeah.
Okay, very good. So this is what I want you guys to put in your own words. Try to summarize it, basically, that in a conductor, what's happening in here, this has to do with how the electrons are drifting inside the metal. These are free to roam. However, they will bump into the atoms from once in a while, and that slows them down. but then they will accelerate. The longer that time, the better the conductor is. Gold is very good conductor, silver is very good conductor, copper is very good conductor, and copper is the one that is used in the industry because there's a lot of it and it's cheap enough to use it. Okay, iron is a good conductor, but not really that great. Okay, we don't use iron for a lot of reasons. Okay, so we use other conductor like copper. Basically, that's what you will find in your household. So this is what's going on in there. Okay. Again, for the AC current, the actual what's going on in here is that you have an oscillation. Okay, so at some point the electrons are moving in the positive direction, and the other time they're moving in the negative direction, and so on. So the polarity flips between positive and negative, and so on and so forth. Okay, so the polarity flips, and that is what is called in DC current. Conductor, any material having free charges, particles that are easily flow through it when an electric force acts on it. Case in point, silver, gold, copper. Is it? Cu, the symbol for it. Oh, I think it's an O. Oh man, I'm used to the symbols. Yeah, okay. CO, yeah, okay. Copper, and then what else do we have? Iron is okay, but not really good. Okay. Not so good conductors as opposed to it are insulators. An insulator, for example, is wood, plastic, air. Otherwise, if air is not an insulator, we have a problem because I have a plug next to me in here and a plug probably next to you, and the charger should be flowing in the air, and that's not good. Okay, so those are some of the insulators that we can I can think of right now. So the difference in potential is really what matters, just like in the difference in pressure. So when they tell you the power company gives you 120 volts, what they are saying actually is that there is a difference. There are two plugs in here. There are two ends in here where you plug the device. The difference between them is 120 volts. This one could be probably 17 volts, and this one could be what? 137 volt. So that when you subtract the two, is going to be 120 volt. Obviously, this is an AC current, so the polarity is flipping back and forth. So sometimes this one will be the higher, this one will be the lower. At the end of the day, this 120 volts, as a matter of fact, this is not exactly correct. This is 170, and this is a negative 170, and it fluctuates between these two values on average, okay? And it acts as if it's a 120 volt, as opposed to this one. This one is actually difference is exactly 1.5 volt. So the bottom one could be 10 volt, this one. The other one is exactly 11.5 volt. So that if you take the difference between them, this EMF, this battery is of 1.5 volt. What matters is the difference in height. So that is exactly what's going on, actually similar to gravity too. So if we have the two levels, for example, of the fluid on the same level, I don't have any difference in pressure. So the fluid will not flow from one way to the other or the other way to the other because there is no difference in height. There is no difference in pressure. But if the minute that there is a difference in pressure, the fluid will move this way and this will move up so that the pressure is balanced. And the role of the battery, in this case, similar to that pump, is just to maintain that difference in voltage. So the minute one charge moves to the other side trying to balance, the battery takes it and move it to the opposite direction so that maintain that difference of 1.5 volt. The battery is as good as when it makes that difference in voltage. The minute the battery fails to maintain the 1.5 volt across its ends, across its terminals, it becomes basically useless. Then you have to go and buy another one because this no longer is good. Okay, so that is really what you're paying for. You're paying for this battery to maintain exactly 1.5 volt across its ends. And that is the agreement you have had also with the power company promising to deliver 120 volt to your household, okay, on a regular basis. So if they fail to do that, they are actually not in compliance. In other words, they failed the part of the bargain because you're relying on the fact that they're supposed to put 120 volt. So if they do put less, then your device will not work. If they put more, they could actually damage your device too. So in other words, that is the agreement between you and them, and you have to provide, you have to operate with that understanding. Again, that is the role of the difference in potential. So the difference in potential is really like the difference in pressure earlier when we saw the mechanical system for it. Here is the mechanical system again, okay? So no flow of charges occur when the potential difference is 0. When you reach the same height, when the two fluids reach the same height, let's say, for example, this is here, oops, here. So this drops to this level and the other one, this drops to this level and this rises to this level. There will be no more motion than a fluid whatsoever. Because if one atom decides to move this way, another one comes from the other side and balances it, and you cannot. There is no need for more motion. And the role of the battery then is to ensure that the minute one drop of fluid moves to this side, trying to raise this one up, that drop actually comes in here. Is pumped by this pump. Okay? And to maintain this difference in pressure. So if this pressure difference in pressure, let's say for example, is 10 pascals, the pump in here has to provide 10 pascals to maintain that 10 pascals. So if the difference in pressure is actually 100 pascals, the pump need to work harder, need to actually operate with 100 pascal now difference in pressure, so that it pushes enough fluid to compensate for that difference in potential. It always has to adjust itself with that. Okay, so that is really the similarity between this system and actually the electrical system. Okay. So again, this is the fluid. The valve in here acts as a switch, the switch that you turn on and off the electricity. Okay. You may have a battery in here, and you may have a resistor in here. This is the symbol for the resistor, by the way, in circuits. But if the switch is not on, then there is no charges moving in each way, one way or the other. Now, like I said before, you have to be very careful with this analogy in here, because if you have a fluid in here, and if the pump is running, let's say, for example, at 100 pascal, they use the PSI. I know they don't use the Pascal and for the daily applications. If it's running with that much power and the valve is closed, could cause damage to the pump or cause damage to the pipes or something like that. Whereas in here, it's on all the time. Okay, so you cannot really, you have to be very careful in here, okay, with this analogy. But the valve in here will act exactly as the switch in here. Furthermore, there is another property of the valve that you cannot do with the switch. The switch can be on and off. This one can be on or off, and in between. We can actually adjust the power in here too. So this analogy cannot really be pushed too far to the mechanical system. So again, here is a schematic of what that circuit looked like, okay? With a battery holder. And the battery in here is going to provide the charges. Now, when the charges go through a resistor, like for example, the light bulb, they will cause it to heat. So this is called actually, because they will be moving in like a filament of tungsten in here. That's the material that is used inside. That element in here, when that filament actually, when it gets too, because there is power dissipated in the resistor proportional to the square of the current. So if the current now is even a small value, will cause a lot of power in here, and that power is a so-called Joule heating. And the Joule heating is actually what you feel yourself when you try to plug a device that is, you try to unplug a device that was connected to the wall, you will feel it hot. Except now it's extremely hot to the point that it glows. That's why you use tungsten, because it's so very sensitive and it's actually very small diameter, because then very little power in it can actually glow and emit radiation. And that's exactly the light that you get from the light bulb, okay? So What kind of energy is in here? It's a chemical energy. So the people who build batteries, and Volta was one of them who actually designed the first one, they use a chemical process because here is the problem. Let me explain to you the problem, exactly what's going on in here. Let's say, for example, a charge left in here, okay? And it went through this circuit, it caused this heating, and it came in here. This is a negative, and that is positive. So the positive, when it comes in here, it wants to be happy to cancel the negative, and we're done. Because there was an excess of positive charges in here, on the positive side, an excess of negative charges in here. So the minute one of these positive charges decide to go through the circuit and come and close itself in here, it's going to meet one of the negative charges and cancel it. And that's it. That's all there is to it. That's all you want. But then there is another charge in here that decides to do the same migration in here and come in here and find another negative charge, and they will cancel. And that's fine. But the problem with it, if you do it this way, is going to only operate once and that's it. So what the battery does, and it has its own power for that, is it uses a chemical process to take this charge from where it needs to be, where it wants to be, to a place where it doesn't want to be. It doesn't like to be in here because it's too crowded already with positive charges. And you want to add it there, that is not going to be a happy charge at all. Okay, same thing. This charge in here that came in here and canceled this negative is actually going to be yanked and actually put in here. And each and every one of them, they don't like to be here because there are positive charges already. Let's say, for example, we start with 10 positive charges and there was a negative 10 positive charges. One of them migrates in here. So the one that left now will make it 9. And the one that came in here now negative 9 because one of them canceled for the negative 10s and I'm left with negative 9. So the battery now drops in voltage from 1.5 to less because I have less charges on this side and less charges on the other side. So what the battery does, if it's still good, it's going to take one of these positive charges internally and move it to this side so that it's going to make it a total of 10 still. And since it removed 1 from here and there was negative 9 to begin with, so there will be a total of negative 10 to remain and maintains the voltage across its ends. Okay, maintain the voltage across both ends because it keeps those charges balanced as long as it has chemical energy in it. The minute the battery starts to falter, starts to fail, basically the charges will come in here and it cannot drag them against their will to where they don't want to be, and they start to cancel in here. The minute that voltage starts to drop, at some point there will be positive 8 and negative 8, and down the road it's going, so the voltage drop from 1.5 to probably 1.2, and then it's going to be positive 7 and negative 7 to 1.1, and at some point it becomes non-operational, even though there is some charges remaining in here and in there, but it's really because it's not going to push enough current to cause this glow. It's not going to push enough current to make the device work. That is the time when you dispose of it, hopefully in a clean fashion, in an environment-friendly fashion, and you go and get another one, okay? And the process continues. Make sense? Good?
Yep.
Okay, very good, thank you. Again, I mentioned the resistors. The ones that I showed you guys look like this one. It's color-coded, okay? And then this one is actually a variable. It's called a potentiometer. There are actually different values in here for the resistor depending on which end you're going to connect it. So different fashions for the resistor. The symbol for it is this basically in circuits. So when you're looking at a circuit and you want to know where are the resistors, look for this symbol. So that is the symbol for the resistor, okay? So how is the resistance in here? Obviously, the length affects it. The longer the wire, the more resistive it is. Because it takes so long, more and more collisions before charges come from the other side. The cross-section also plays a role. the wider the area, the more charges can flow. The narrower the area, the less charges can flow. Think of a highway, for example. You are on the interstate, for example, with 4 lanes. And if all of the 4 lanes, let's say, for example, 1 or 2 lanes are closed in up front, obviously, initially you have this many cars flowing, but now you have to squeeze them through 2 lanes only. So it's going to basically have there will be slow down in the traffic at that point. So that is exactly what this area thing is. Okay. So the resistance is grows with the length, and inversely changes with the area. That means if the area grows, the resistance go down. Okay. If the area shrinks, the resistance will go up. Okay. And the type of material also. The type of material actually also plays a role. Symbolically, and you may see that in the book, it's written as the rho, which is a property of the material. How inertly, how inside of it is actually resistive, times the length divided by the area. So this is how the expression for the resistance is. Okay. So again, this is the filament I was discussing earlier for the light bulb. The resistance changes with temperature, so it's basically impacted by temperature, and that's why we have this. We take advantage of that, because if it changes with temperature, and actually there is heat that is going to come from it. So in this case, we use that to our advantage for it to glow. Okay. Okay, there are other kinds of materials that are actually, in addition to conductors, and that is the other topic that I want you guys to please list it in the bottom. So the conductors, I already mentioned insulators. There is this kind of materials which are called semiconductors. And semiconductors are the ones that really do not conduct electricity unless you do proper doping for them. And the doping will make it so that either conducts with the charges, negative charges, electrons, basically, and those are called N-type doping, or the P-type doping, which is positive doping, in which case is actually the lack of electrons that moves are also called holes. And the material that I mentioned earlier is one of them. So the diode is actually a typical semiconductor, okay? And the fourth one and the final one are actually superconductors. Superconductors are special materials that conduct with no resistance whatsoever when temperature is low enough. Okay, the 2 main things in the periodic table that play the role of semiconductors are silicon and germanium. Okay. So again, I mentioned superconductors, material with 0 electric resistance to the flow of charge. Flow of charge is without generation of heat, basically. This is still an ongoing topic, trying to build high temperature superconductors, and research is ongoing trying to do that, okay? Ohm's law relates the current, the voltage, and the resistance. Symbolically, and again, you will see that part of your assignments, is that the voltage is equal to the resistance times the current. So this is the expression of Ohm's law. This is a major law for circuits in general. So again, here is the expression. Voltage is resistance times current, or current is voltage over resistance, okay? Because of this relationship, resistance can tame the current. So you don't want too much current flowing through a circuit, or probably you would want it the opposite way. So they're an essential component to it, okay? Damaging effects of the electric shock to the human body, because then they can have a huge current flowing through your body that can cause heart attack, basically stops the blood from flowing. The reason why the bird isn't affected is because you really need a difference in potential, and it's sitting on the same potential, okay? Here is the difference between the DC current and the AC current. The DC current basically is constant. okay? And it always moves from. So basically here is a battery, positive end and the negative end. So what's going on in here, the current is flowing this way, but you and I know that the electrons are moving in the opposite direction. So the fact that an electron moves this way means that the current, which is a positive basically charge, is moving that way. That's all. So the electrons will leave the negative side of the battery, which is called the cathode, and end up in the positive side of the battery, which is the anode. So what I was describing earlier in terms of the picture of what's going on between positive charges and negative charges, in actuality, it's the opposite. The electrons are leaving actually the negative. So once they come in here, there is a depleted region of electrons. So there are a lot of positive ions sitting in here. So when an electron comes in here, it cancels one of those ions, and that's the end of it. Except the battery doesn't like that. It wants to maintain its voltage. So it's going to drag that electron and move it to where there is a bunch of electrons already accumulated in that region. So it's going to move it against its will in there. And then this process continues. As long as the battery is still good, that's how it is. Now, if I think of it in terms of positive charges, the picture is the reverse, that's all, okay? For the AC current, it's changing, it's alternating. That's the A stands for, alternating. Okay. Worth knowing, the United States in here operates with a voltage. This is an effective voltage, not a real one. So this is effective, okay, as if really 120 volts. This is what matters when it comes to power. That's why we use this one. This is the frequency in the United States, 60 hertz. And in the rest of the world, for Europe, for example, they use 220 volts, and the frequency actually is 50 hertz. Okay, 50 hertz. So the currents, and that's why you need an adapter if you're traveling overseas. Okay, I showed you a picture of a diode earlier, and this is how they would look like. So this is, again, you can take one of these devices, for example, a diode, or 4 of them, and you can make a current, because at the end of the day, it's cheaper to make an AC current. It's easy to work with an AC current. And if you have to run an AC current through a transformer, you have to be an AC current. It cannot be a DC current. So for example, the power company delivers a huge voltage high, and then when it comes to your neighborhood, drops it down. When it comes to your household, it drops even down to 120 volts. But when you're going to connect it to your phone, for example, to charge it, the phone doesn't operate with 120 volts. It operates only with 5 volts or something. So in this case, you need even a transformer, which is usually inside your plug itself. And that is the device that you're going to use that is going to bring down the 120 volt down to 5 volt. So that's why you need to have an AC, because this operation cannot operate with a DC current. But then at the end of the day, the phone actually uses a DC power. So you need to convert that to a DC power. For that, we can use diodes. Okay, diodes, they have this property that they can connect. They have 2 legs. They can, if you send a current through them in one direction, they can take it, but if you send it in the opposite direction, it will not. So take advantage of that. So the current in one direction is canceled. So this is a diode. I'm trying to see if you can see the 2 legs of the diode. Okay, this is a red diode. It's not that's what basically indicates one side and the other. Now to connect them properly. Anyway, so this is used to regulate current. Let me share with you the screen again. Share. Okay. So this is how the current comes in as an AC current. They will kill it when it's negative, and then will allow it when it's positive. If you do a lot of them very close from one another, if the frequency is high enough, it will act as if it's a DC current, and now your device, your phone, for example, can operate. So what's going on in here is you need an AC current, because that's how you produce it. You produce it by rotating basically turbines, and the rotating turbines will create a current positive one side and negative to the other side. Then you up the voltage to a high voltage lines to deliver the power to the city. When the city comes into your neighborhood, they bring it down from that super high voltage to a lower voltage, and then they deliver to your house, in that case, using 120 volt. Now, your device is not going to operate with 120 volt AC current. It needs actually a lot less. Your computer probably needs 19 volt or something, your laptop that is. So it's not going to require, it's not going to work with 120 volt. So it needs to actually, the charger that you plug to the wall usually is actually a transformer. So it's going to bring down the voltage to the value that you need. And at that point, all of that process needs an AC current up to that point. Transformers do not operate with a DC current. At that point now, you have a 19 volt that is looking good now in your device, like for example, this one. Okay, this is the power supply. This is where the power comes in. Now you have whatever is required for, oops. I'm sorry, here it is. I gave you the wrong side. Here is where you plug into the wall. Okay, let me go back in here and stop sharing. So here is a device I'm trying to show you. So this is where you plug the device to the wall, and immediately next to it, I don't know if you can see it or not, next to my finger in here, there is this many turns. Actually, that is a transformer. Okay, there is this one, there is this one, there are these two in the back in here. Those are actually what operates as transformers, or at least they act as if they're transformers. They change the voltage, and there are some actually capacitors in here, and more devices in here. There are resistors actually all over the place. But the power supply in here, this cannot operate at 120 volt. So you need to connect it to a device to bring the power down to a lot less voltage in here than what the power company requires to do. Okay, so this is where the power supply is. Okay, this is actually an Arduino board that operates in a similar fashion. The power supply is actually here too. Okay, that is where it's coming from. And the Arduino Uno, this is another device that I have in here. Anyway, so let's continue with this one. So the as a diode in here, it's essential for this operation, because the power company cannot deliver to you nothing but an AC current. Again, this is the picture I drew earlier. So if you missed the point of the discussion, the first one, here it is. Okay. Again, this is exactly what I was talking about. They're accelerated, but then they bump into the anchored metallic ions, which they lose all of their energy, and then they keep on moving until they reach to the other end. So they're not bumping into one another. They bump into actually the ions. That's another misconception that's very important to remember. The power company does not send you electrons. They send you just the difference in potential. The wire that you use, this wire that you use in your household, whatever wire that you happen to have in your household, is already comes with its electrons. So the electrons now are pushed from one way to the other, collected from the other side, and continuously the difference of potential, the one that is continuously pushing them one another, which makes that analogy earlier with the water not also correct, because that analogy with the water, the water company actually delivers water to your house. Okay, when you go to the store and buy, for example, a pipe and a conduit for water, you don't buy the water with it, you just buy the conduit. Whereas if you go and buy from the same store a wire, for example, a copper wire for your house, it comes already with its electrons. So that's something that you have to be careful with. So the power, by definition, is the current times the voltage. So that is exactly how much we're supposed to be responsible for. Okay, this is the rate at which energy is consumed. The unit for the power is watts. So when you say it's 100 watt or 60 watt, that is the unit for which. There is also another way of also expressing it actually in terms of joules per second. Okay. So incandescent lamps, like the one that I was, light bulbs, the one that I was discussing earlier with tungsten, they dissipate a lot of energy. That's why these ones are actually more efficient, because they have a rating usually of power a lot less. For example, they tell you this one is this many watts, but operates as such and such thing, because the luminosity at the end would matter. That LEDs like this one in here actually is an LED too. Diodes are actually LEDs too. Okay, so those are, they use different properties in here for light to be emitted from one end to the other. Circuit, and we've been talking about it earlier, is how you connect basically device on a closed path in here. Okay, so there are two types of connections. There is either the series connection, where basically you start from one point, you go to one device, you exit that device, you go to the next device, and then you exit to that device and you go to the next device. This is usually not typical in households. Households, they have the parallel. So basically, if you look at any plug in your household, it's 120 volt, meaning that this one and that one, both of them, this one and the one below it, both of them have 120 volt. They are not one after the other. They are actually next to one another. That is why it's called parallel connections. So here is how they would look. This is a series, as you can clearly see. I leave the battery, it go to this light bulb, jump from this light bulb from the other side basically of it, and go to the next light bulb, then jump from it, go to, so if I am a charge, for example, moving, I go through the first light bulb, the second light bulb, the third light bulb, and then come through the switch in here, which need to be closed actually for the charge to come back in here in the battery. The minute this the charge closes the circuit, it has to continue in this fashion. Okay, obviously what's going on in here is that the charge, let's say for example, 10 charges, 10 coulombs, started moving. The 10 coulombs, the same 10 coulombs will go through this device, through this device, through this device, and then come out through the switch and are collected back in here. So the current is the same. However, the voltage drop depends on the resistance in here. So the voltage is not the same. So if there is 1.5 volt in here and I have 3 of them and they're identical, I have to divide it by 3. So this one will have a half volt, this one will have a half volt, and then this one will have a half volt. Okay, so that's a key point in here when it comes to this thing in here. So again, this is just a repetition of what I was talking about. A parallel, on the other hand, look at this. If I have, let's say, for example, 15 coulomb. The 15 coulomb, the minute it's going to hit in this point in here, it's going to be split. And it's going to be split between this, some of them will go this way, some of them will come this way, and some of them will go this way. The switch actually is open in here. So the fact that the switch is open, there will be no current flowing through this one. So the 15 that comes in here are going to be split in here depending on how much resistance in here. If they are the same resistance, then they will be splitting evenly. If they are actually different resistance, then they will split different ratios depending on the easiest path where the most of the charges will go. Depending on the least resistance is when the path of the charges, the highest charges will go. The path of the highest resistance will actually see the less charges go. This has actually an infinite resistance. So when a circuit is open like this one, it has an infinite resistance. So there is no charge in here that's going to flow through it. So the charges will split themselves in here. This configuration is a parallel configuration. The voltage is the same. The voltage between this node and this node is the same point in here. So if it's 1.5, it's 1.5 for all 3 of them. So the biggest difference between a series circuit and a parallel circuit is that in the parallel circuit, the voltage is the same. The current is not. As a matter of fact, it's 0 here. In the case of a series circuit, the voltage is not the same, but the current is the same. Because if I put a switch in here between these two resistors or two light bulbs, and if I open it, there will be no more current at all. Everybody will get 0 current through it. Okay, or everybody gets the same current, 1 amp going through them, for example. Okay, so the current is the same, the voltage is not. This one, the voltage is the same, the current is not. That is really the biggest difference between parallel and series circuits. Okay. Again, this is just checking the ideas in here. So this is, I mentioned earlier, what's going on in your household, okay? So all of the voltages actually are 120 volt. That means that they're actually in parallel. I mean, you may connect, like for example, for Christmas decorations, you may connect things in series, okay? And you may connect things in series, but that's, you have to be very careful with. Most of the times the plugs actually, the dividers, they come in already in parallel, okay? Which means that the current could drop, because the current is not the same in parallel. The voltage is, but the current is not the same, depending on the path of the least resistance. So it can overload, in which case then you have to be very careful with it, because if there is a huge resistance on one side and less resistance on the other, so the current can actually go through that one and cause damage to it. That's why usually you have circuit breakers and you have circuit fuses to prevent that thing. When they notice that there is a current going through the other side, they themselves will conduct and take all the heat for it and can cancel basically the current altogether in that section of the circuit, okay? This is in a nutshell the chapter, okay? And if you guys don't have any questions, let me stop the recording and I will see you guys on Thursday. Sounds good?
Yeah, getting back into it.
Okay, very good. I'll see you guys, okay? Thank you. Let me stop recording.